Welcome to Bot Thoughts by AmtocSoft. I am Alex. 3 months ago, I watched a customer support agent confidently give a user the wrong refund policy. The same policy it had been corrected on 14 times in the previous 2 weeks. Each session started fresh. The team had built the agent to be stateless because they were worried about the operational complexity of a vector database, and that was a reasonable call at the time. But stateless does not mean no side effects. It means all the side effects land on the users, who keep getting the same wrong answer and eventually stop trusting the agent entirely. That incident pushed me to find a middle path. This episode is about that path. Let me walk through why stateless agents break, because the failure modes are specific and they are worth naming clearly. The first failure mode is re-asking answered questions. An agent with no memory of a previous session asks for context the user already provided. The user has to repeat themselves. In a support context, this is immediately frustrating. It signals the agent does not know who you are or what you previously discussed. The second is corrections not persisting. A user tells the agent something is wrong, or gives it a preference, or corrects a misunderstanding. The agent acknowledges it in the current session. Next session, it is gone. The 14 correction support bot I mentioned is the extreme version of this. 14 separate interactions where a team member corrected the refund policy, and every correction was thrown away at session end. The third is long workflows losing their decision rationale. Some agent tasks span multiple sessions, a code migration, an onboarding flow, a multi-day research task. Without memory, the agent cannot reason about why it made certain decisions in previous sessions. It has to start from first principles every time, which means repeated setup cost and the risk of contradicting earlier decisions. The fourth is users abandoning the agent entirely. Stateless agents create learned helplessness in users. After enough sessions where context is lost, users stop volunteering information because they have learned it will not be retained. The agent becomes less useful over time, not more. Now, the team's reasoning about stateless design was not wrong. Stateless systems are easier to reason about. They do not accumulate drift. They do not require maintenance of stale state. All of that is true. The mistake was treating stateless as the only alternative to a vector database. It is not. There is a middle path, and it uses tools most teams already have. The middle path is 3-tier episodic memory, built on SQLite and LLM summarization. Tier 1 is the raw event log. Every interaction, user message, agent response, tool call, correction, preference statement goes into an append-only events table. This is the source of truth. You never update or delete rows during a session. The log is immutable. Tier 2 is episode summaries. A scheduled job runs an LLM compression pass over batches of raw events. 20 raw events become one dense paragraph. A well-written compression prompt, and the wording matters, produces summaries that capture specific names, decisions made, corrections applied, and commitments given. The LLM is genuinely good at this task. The result is roughly an 80% token reduction. 20 events that might be 4,000 tokens compressed to a 200-word paragraph. Tier 3 is working context. When a session starts, the agent gets the last 2 episode summaries plus the current session's unarchived raw events injected into the system prompt. That is the agent's memory. It is compact, current, and specific. What makes this architecture work is a key insight about what agent memory actually needs to be. Most agent memory is a recency and keyword problem, not a semantic similarity problem. You need to know what happened recently with this user. You need to be able to search by name or topic. You do not need vector similarity across millions of embeddings. SQLite's FTS5 full-text search extension handles the keyword retrieval problem with no embedding infrastructure, no separate service, no model to maintain, and no API calls at query time. Let me walk the schema, because the schema is where the design decisions become concrete. You have 2 tables. The events table stores every raw interaction. It has an ID, an agent identifier, a session identifier, a timestamp, a role, user, assistant, or tool, and a content field with the text of the interaction. There is a created at timestamp and a Boolean flag indicating whether this event has been archived into a summary. The summaries table stores the LLM-produced episode summaries. It has an ID, an agent identifier, a creation timestamp, a summary text field, a window start and window end, the timestamps of the oldest and newest event covered by this summary, and an event count. The FTS5 virtual table is an index on the events table's content field. Creating it is a single SQL statement. After that, full text search across your entire event history is a standard SQLite query. No embedding model, no cosine similarity, no separate search service. The three indexes are the whole performance story. Events indexed on agent ID and timestamp descending. Summaries indexed the same way. With those two indexes, retrieving the working context for a session is 2 index scans, most recent summaries, most recent unarchived events. On a database with a year of interaction history for 100 users, that query completes in single-digit milliseconds. One design decision that matters: the window start and window end timestamps on summaries. These let you reconstruct exactly which events went into any given summary. If a summary is inaccurate, if the LLM compression produced something misleading, you can identify the source events and understand what went wrong. That auditability is important when you are storing information that affects how an agent behaves. How do you decide when to run the summarization pass? There are 2 strategies, and the right one depends on your traffic pattern. The first strategy is schedule-based. Run the compression job after every N interactions, or on a time interval, every hour, every day. This is predictable and easy to reason about. The downside is that in high-traffic periods, you may accumulate more unarchived events than fits in your context window before the next scheduled run. The second strategy is a token budget trigger. When the unarchived raw events for a session would push the injected context over a threshold, say 2,000 tokens, run a compression pass immediately. This is adaptive. It ensures the working context never blows your context budget, regardless of how much activity has occurred. The downside is that it adds latency at session start if compression needs to run before the session begins. For most production deployments, the token budget trigger is the right default. It is the one that prevents the worst failure mode, an agent that gets slower and more expensive as a user becomes more active, because their unarchived event log is growing without bound. Now let me say something about the compression prompt, because this is where most implementations go wrong. A prompt that says summarize the key facts from these interactions produces vague, generic summaries that do not actually inform the next session. A prompt that says summarize into a dense paragraph of key facts, including specific names, products mentioned, decisions made, corrections applied to agent behavior, and commitments given produces summaries that actually reduce errors in the next session. The difference between these 2 prompts is the difference between a summary that says the user discussed refund policies and one that says the user corrected the agent's claim that refunds require a receipt. Refunds do not require a receipt for orders under $50. The second version is the one that prevents the 14 correction problem. Let me share the production numbers from 6 weeks across 2 deployments, and then close with the broader lesson. False recall rate, agent confidently stating incorrect previously corrected information, dropped from 40% to under 8%. Context size at session start dropped from a 12,400 token median to a 4,800 token median, a 61% reduction. Both of those numbers come from the same architectural change: episodic memory with LLM compression rather than raw event log injection. A few production considerations worth flagging. Backup is trivial. SQLite is a file. You copy it. Compare that to the operational burden of backing up a vector database deployment with its own service, its own data format, and its own restore procedure. Concurrency, enable WAL mode, write-ahead logging. This is a single pragma statement. It allows multiple readers while a write is in progress, which is the access pattern you get when multiple agent sessions are running concurrently against the same database. Privacy: the events table contains user conversations. That means it contains personal information. Encrypt at rest: if you are handling data for multiple users with different isolation requirements, use per-user database files rather than a single shared database. The FTS5 index and the working context query work identically whether there are 10 users or 10,000. Schema migration: add columns with defaults, never remove columns from a running agent. Removing a column from an active system requires a migration plan and a deployment window. Adding a nullable column with a sensible default can be done at any time. The lesson from the 14 correction support bot is not that you need a vector database. It is that stateless agents have state. It just lives in the user's frustration instead of your database. SQLite episodic memory is the smallest system that gives you a real memory layer without the operational complexity of a dedicated vector store. Full schema and memory store class at github.com/amtocbotdroid/amtocbotexamples/agent memory SQLite. Blog 267 has the full walkthrough. Long-form video V041, shorts S162 and S163. Subscribe to Bot Thoughts. I am Alex, and I will see you next episode.